Good day everyone. Today I will present my paper called the Finite State Machine Base Finger Pulse Tracking. My name is Noorkholis Luthfil Hakim. I'm from the National Central University, Taiwan. Okay, we'll start this presentation. And this is my outline. First, I will introduce our system, then we'll go through the methodology. The first is a hand sample data collection and how to do the normalization of this data. The second one, I will go through the finger pulse clustering to create the finite state machine system. Then I will go through the main algorithm, which is the finite state machine, the builder, and the finite state machine runner. And then after explain the methodology, I will go through the experimental result and discussion. Then I will go to conclusion and future works. In this work we are focused on the one model and to detect the finger pulse on repeating or limited hand gesture actions using a finite state machine problem. So we use the finite state machine algorithm to try to solve this repeating and limited hand gesture or hand action system. This is so we propose the novel finger state machine finger tracking, novel finite state machine finger tracking method. And this method have two main algorithms. The first is generating the finite state machine and running the finite state machine system itself. The idea is to keep tracking the hand by using the finger by using appearance-based method, finger detection and tracking, then use it as the one of the features while replacing the finger position with the result from the finite state machine system. The finite state machine builder proposes to build the finite state machine from the sample hand action or hand gesture that we record, and then this is to represent the whole movement of the action in one set of finite state machine system, while the other algorithm, which is the finite state runner, is using to find and let the system run between the states, finding the correct next state and produce the correct finger position correspond to the input. Our methodology here, as I said before, have two main algorithms. The first algorithm is using to build or generate the finite state machine using set of sample gesture in one action. The second one is using to run the finite state system with appearance-based finger tracking system that we already have in the previous paper. Then the next session we will explain the both of this methodology in detail. Here after this is our system architecture. Here you can see that we have a RealSense camera. This is a 3D camera, and from the RealSense we extract the point cloud and RGB image. In the point cloud side we use the finger detection and you extract the finger features, and then the RGB side we have the HOG descriptor here, and we combine these two features into one. Then in the recorded side we use it to train and build the finite state machine system, and after that we get the finite state machine model. And with combined feature we used to running the finite state machine runner, and then we using the finite state system that we have, we can predict the next state function and get the correct finger position. So before everything we try to create the finite state machine system itself. So to do that we need to sample some hand gestures. So need some sample of the hand pose data of specific action, and the sample data that we extract, we record. We got the point cloud data XYZ and the RGB mix, which is XY. The sample data will be labeled its finger position, and the semi-manual method was used in here. Given the point cloud, our previous finger detection method and tracking was used to select to extract the finger position from the point cloud. The missing finger and the wrong wrong label finger will be corrected using a manually selected by a human. So we use the finger 3D selector application that we built to fix the finger position and some finger missing. Using this application, the user could select the correct position of the finger in three-dimensional space. So here, the right side is our 3D finger selector application, and this is the left side. This is our example. The first we have the raw point cloud without the finger in there, so we use the raw finger tracking to get the finger position. Some finger position is not detected correctly, so we need to fix it using this application, and then we can get the full finger detection marker in the fixed finger here in the picture. And next is to normalize the data, the previous data that we collect. And here we have three steps. First is subtracting each finger with its palm to bring it to the original position. Then find the scale factor of its hand. And then we resize the size of the hand by dividing it with the scale factor. So we use three equations below that picture. Then we do the finger pose clustering, and to build the finite state system, we need to represent the hand sequence into set of states. For each state is represent one hand pose. So we may record many hand poses, and sometimes it have a similar hand pose. So we need to put a similar hand pose in one cluster as to represent as one state. And to do that, we use the angle of the fingers that we manually mark, semi-manually mark it as a feature since it's robust to rotation. Then we use the equation below to extract the angle representation of the hand. And using this angle feature, we use a simple clustering method using accordion distance algorithm. And for threshold, we calculated by experimenting the sample data. So by this, using the finger pose clustering, we got the few state or hand state, you call it. Then to represent for each state, we need one representation of the finger pose. So we average the clusters, the hand that have the same clusters. So we call it the clusters member, and we average it, and we got the one representation of the finger or hand for each state, and we call it the state hand. And the next slide we will explain the finger clustering method. So here we have a sequence of the sample cases for one set of action. We do the clustering from previous slide. Then we got a bunch of state, which is the size is lower than the sample sequence. So for example, we have a 300 sample sequence, and we may have a very limited action. So after we do clustering, we may have 6 states in here, for example. And then after that, we fit the the sample to the FSM builder. In here we try to build a finite state machine model in one action or one gesture. The finite state machine model, and we got the state already, so but we need the connection between state to make the system could in between state, running in between state, and we call this a state transition system. And there are two ways to create a state transition. The first is based on the distance between the state hand. The second one is based on the time difference. Using the below equation, so we can combine this the method. So the based on distance means that we calculate the distance between the state hand, and if it's close, then we connect. We give the connection for each state. The other the time difference means that for each cluster's member, it have a time difference with the other cluster's member. So if it's a time difference, means a time difference in the frames. And if it's the time difference, for example, is 1 frame or 2 frames, then we will make it like it's connected. These two states is connected. Here's the example. So we have a state without the connection or the transition system. Then we use the decision tree to train and our sample, and then we use then we got the state transition with using the two features from below from previous slide. Then we can get the connection between the states, and here you can see that there's a state transition system here. So the main purpose of this system, which is now we go to the FSM runner. The main purpose of this FSM runner is to estimate the corresponding finger position by running through the FSM model that we previously built. The system starts by first selecting the initial state, then select the next state by using the next state function that we will build. And the next slide will be the detailed architecture of the finite state machine runner system. Our system have two mechanisms. We use the two algorithm. With the first one is the big tree mechanism. Second one is the small tree mechanism. The big tree used to select the initial state of the gestures, and the small tree system used to detect the movement of the finger. So the big tree means that we can jump around the state without the state transition restriction. For the small tree, we need to follow the state transition restriction. Here the architecture. So here we use two features, which is the finger features and the HOG descriptor. We combine these two features, and first usually we use SFM big. We use a superfactor method. So SFM big tree to search the initial state. Then we use the SFM small tree in the next frame to get the correct finger position. As seen in the architecture, we use two features as the input, 3D point cloud and 2D RGB image. The finger precision from the point cloud extract by using our previous finger detection and tracking method. Then for a 2D feature, we use the HOG and hue moment of the image of the hand. Our finger detection tracking methods may not get the correct result. That's why we use the FSM runner to fix the finger position, and we use the support vector machine or SVM to classify the features into the stage number by using a big tree SVM classification and small tree SVM classification. The big tree SVM classification model is like this. Suppose we have a 6 stage that have its own state transition or connection. Big tree SVM it cannot be restricted by this transition system. So this big tree model can be by using this the system can jump around the state, and like this we have 6 state and the class result also the 6 class. For the small tree SVM classification system, the small tree is restricted by the finite state machine transition system. And for example, if the current state is state 1, then we only can jump to the state, the neighbor of the state, like 5, 2, or 1 itself. And this one of our system using one neighbor as a restricted system. Then the second one is the right one is using the two tips of neighbor as a restricted jump. I can say that one. So for example, if our current state is 1, we can jump to the 5 or 6. In previous we only jumped in the 5, so now we can jump to 5 and 6 or 2 and 3, something like that. So it's have 2 neighbor jump. Because our sample here in our works we only have a small state, so we only use the one jumping example. So for the experimental and result and discussion, here we conduct several experimental to train and testing the robustness of our method. The first experiment is used to find the best combination of the features. We have 3 features that we extract. First is the finger position from our previous finger detection method, and HOG or histogram of oriented gradient, and hue moments, which from the 2D image. From the sample hand pulse record, we train the data and testing it with ratio 9:1 as 10% as testing data. The results show that using combination of the VFD and HOG perform the best. Here we use the big tree SVM as the testing things, so we got 75% recognition correctly in the big tree SVM. Then we use this combination, this best combination to test to the small SVM tree, and the result we got around 83% the small tree SVM, and so the result may not vary, since some states have the similar pulse, so it's hard to distinguish with a small amount of data. So we also need to add more variation data to increase the accuracy of this system. So the conclusion is a novel finger pulse tracking based on the finite state machine algorithm have been proposed. The method have 2 parts. Here the first is FSM FT builder and then FSM FT runner system. There are 2 experiments conducted in the system. The first to select the best combination of the features, and the second one is to test the robustness of the system using the best combination result. And the result of the small tree show that we get 83% in average, could detect and recognize the finger pulse well. And why the result is not very high, this have 2 main reasons. The first is because the feature selected was not enough to represent the hand and finger. and also the variation and the amount of data that we collect is still not enough. So we need to select the appropriate feature. For example, change the 3D finger position into the 3D point cloud. We can use the 3D histogram facet, or we can add one more like optical flow as 2D side of the feature, or we can use the 3D no, we can use the CNN as the classification method. That's it, our presentation. Thank you for listening my presentation today. And if you have any question, you can ask me in my email, which is at gmail.com. You can you want to know further, you can ask the one who present this, and in the place, and you can give me several questions by email. I will try to answer it. Thank you very much. Bye bye.